The Duke engine reforms this linear arrangement into a circle, creating a true axial engine. The standard piston cylinder sets are mounted in a single cast and machined monoblock, revolving slowly around and in line with the crankshaft. The pistons drive a star-shaped element called a reciprocator, allowing all moving parts to operate in a purely sinusoidal or wave-like motion. The reciprocator in turn drives a central crankshaft in the opposite direction, a key to many of the Duke engine's advantages. Instead of the usual complicated poppet valve system, the cylinders themselves slide past ports and spark plugs that are mounted in the stationary head ring. As the cylinder slides past the inlet port, the fuel and air charge is let in. The charge is then compressed before the cylinder is exposed to the spark plug. The charge burns, driving the piston down in a power stroke. The piston then rises again, ejecting the combustion gases through the exhaust port to complete the four-stroke cycle. With just 5 cylinders requiring only 3 spark plugs and 3 fuel injectors, the engine has as many power strokes per revolution as a conventional 6-cylinder engine, but with at least a 30% weight saving and an astounding reduction in the number of parts. Originally conceived and developed by Duke founder Noel Duke, Duke Engines has put together an international team to help develop the concept, including experienced engineers previously at Cosworth Technology, now Marla Powertrain in the UK, and other major engineering companies, forming a highly skilled CAD design, analysis and development team. From an initial proof of concept, the Duke team have now developed their 3rd generation design. A rigorous test program conducted at Marla Powertrain has proved the engine's capability and its exciting potential. Even at this prototype stage, key performance characteristics have matched those delivered by conventional production engines. Recent breakthroughs, now the subject of patent applications, pave the way for Duke to approach engine speeds not previously achieved in axial engines. Potential applications of this axial technology go beyond just the Duke engine, opening up further opportunities for this evolving technology. Duke's developing engine technology enjoys a number of fundamental advantages over conventional 4-stroke internal combustion engines. Its compact combustion chamber has no hot exhaust valves present and is remarkably resistant to pre-ignition of the fuel-air mix. It can utilize a higher compression ratio, delivering greater power for a given amount of fuel. Spark ignition Duke engines have run compression ratios as high as 14:1 on 91-octane fuel without detonation, delivering a large improvement in efficiency that leads to lower fuel consumption and hence lower overall greenhouse emissions.
The 5-stroke concept utilises 2 fired high-pressure cylinders operating on a conventional 4-stroke cycle, which alternatively exhaust into a central expansion low-pressure cylinder. This low-pressure cylinder harnesses additional work from the expanding exhaust gases, which is discharged directly to the exhaust system in a conventional 4-stroke diesel or gasoline engine. By utilising a low-pressure cylinder, an optimum expansion ratio can be selected independently of the compression ratio. The additional expansion and extraction of work from the exhaust gases results in a lower exhaust temperature. This in turn reduces thermal loading on exhaust components and eliminates any requirement for cooling via overfueling at high power ratings, and this of course significantly improves real-world fuel economy. The principal benefits of a 5-stroke gasoline engine are increased thermodynamic efficiency due to the extra work gained by harnessing more exhaust gas energy, a large overall expansion ratio approaching that of a diesel engine but with gasoline fuel, minimised pumping work due to the downsizing effect from highly rated cylinders, a high rating yet small compact size, up to 20% lighter than existing production engines of a similar rating, lower exhaust temperatures, therefore improved thermal management in vehicle and increased flexibility for exhaust system specification. For example, variable geometry turbochargers can be used. employs current manufacturing technology, so no unique or expensive manufacturing process is required. The five-stroke concept was invented by the Belgian inventor Gerhard Schmitz, and Ilmor has now proven the theoretical benefits with a 700cc turbocharged three-cylinder prototype engine. This engine produces 130 brake horsepower, equivalent to 185 horsepower per litre, more than 160 newton meters of torque, and yet only consumes just over 220 grams per kilowatt hour of fuel.
We have a wheel with a bunch of our spore samples around it, and half of our wheel is placed into a humid environment and half of it into a dry environment. Because our spores are expanding when humidity is high and contracting when humidity is low, that means you have a very tiny mass imbalance on the wheel, which causes it to push forward for as long as the humidity is high in one half and low in the other half.
Once you have a rotating device, you can use it for many interesting applications. You can maybe create a car. We connected the rotating circle to wheels, and the device started to move just like a toy car.
I was so excited.
Wow.
You have the device here, it's not moving, it's not animated, it's dead. And then you feed it some water, and within seconds it comes to life, it starts to animate.
You can do your physics calculations, but when you actually see it turning, it's a completely different thing. There's an invisible power that is going through it.
It's magical.
This little engine looks like it has only 3 pistons, but in fact it has 6, sharing only 3 cylinders. With the help of modern technology, California-based Acates Power has given new life to the concept of the opposed piston engine, mostly abandoned after the Second World War.
With the opposed piston engine, you're able to achieve the efficiency of a much larger engine in a much smaller package.
An opposed piston engine is a 2-stroke engine with separate oil flow. It has no cylinder heads and no valves, both sources of considerable loss of heat and power in conventional combustion engines. 2 pistons move against each other in the cylinder, compressing a fuel-air mixture which self-ignites, pushing the pistons apart, generating power. Exhaust gases escape through ports in the cylinder walls. Stripped of many conventional engine parts, the opposed piston engine is inexpensive and simple to manufacture.
We make sure that we don't over-scavenge and achieve a very good combustion efficiency so that unburned hydrocarbons and emissions is reduced to a great extent.
The layout of a free piston engine combines 2 opposed combustion chambers and a common mover with a piston located on either end. A linear motor generator is integrated with the mover. Used as a motor, it helps start the engine and its movement directly generates electrical power. A free piston design is over 30% more efficient than conventional rotary engines, with proven thermodynamic efficiencies of between 40 and 50%. By removing the crankshaft and crankcase, a free piston engine is more efficient, cheaper to manufacture, compact and easy to maintain. The configuration offers full control over the fuel injection, spark, intake and exhaust valve parameters, and by controlling the linear motor generator, the system can be used to accurately position the piston during the cycle. When shown on a pressure volume diagram, this maximizes the enclosed area in comparison to a conventional reciprocating engine. This means that more useful energy is extracted, improving efficiency and fuel economy. Piston position control can also exploit the potential of a whole range of conventional, sustainable and future fuels with only changes to software rather than hardware. These factors make a free piston engine the ideal solution for next-generation, ultra-high-efficiency range extenders. The 4th generation free piston engine research prototype is currently under test at the Sir Joseph Swan Centre for Energy Research at Newcastle University. It has been designed in collaboration with SR Technology Innovations to validate models, establish a robust control strategy, characterize and optimize the engine performance, and support the optimization of future designs. The Joseph Swan Centre is the highest cited research group in the world on free piston engine technology and has been developing prototype systems for 15 years. SR Technology Innovations has a track record in building new energy technologies to improve low-carbon vehicle performance and develops concept designs through to vehicle demonstrators.
This is the 1906 Adams Farwell. It was built in Dubuque, Iowa by the Adams Manufacturing Company. Fay Oliver Farwell, chief engineer and supervisor. Mr. Farwell loved the idea of these rotary engines. So what you have here is a 5-cylinder rotary engine that spins on its own axis. The crankshaft remains stationary and the entire crankcase rotates to drive the automobile. It's atmospheric carburetor. Feeds in through a little box here of Mr. Farwell's own design. The fuel is brought down through the center, out through these channels here into the cylinders. Then it exhausts on the bottom stroke as the piston passes back through bottom dead center. It ports open and exhausts through this pipe here.